Let's have a look at another question involving AP electricity and magnetism. Here we have a circular loop with radius 0.1 meter. So let's just write the data as and when we read. So the radius R is 0.1 meter. The resistance capital R of the wire is 50 ohm, which is held in place horizontally in a magnetic field B at an angle of 60 degrees with the vertical. So the area, the angle that the normal to the surface makes with the magnetic field lines is 60 degrees. This is going to come in handy or useful when we are going to calculate the flux. So here value theta, we rewrite theta. Value theta is 60 degrees. Now moving on, I think that's all the information we have been given. The magnetic field in the direction shown is given by a function that is B is equal to, so let us write down, B is equal to, A is 4 here. So 4 into 1 minus B is 0.2 per second, okay, 0.2 into T. So from this equation that is given, it is evident that the magnetic field strength is decreasing with increasing time in the direction that is given. So this B is not a constant value, it is decreasing. This is very important. Let's understand this and let's answer the questions. Part A asks us, derive an expression for magnetic flux as a function of time. Magnetic flux here, since we're not given limits, there is no need to write the integral formula. We'll just write the trigonometric formula. Flux phi is equal to field into area into cosine of the normal, or the angle between the normal and the field lines. So here the field strength is B, or flux density B, into area is that of a circle, into cosine of theta. So B here we already know is 4 into 1 minus 0.2 T, into area is pi r square because it's a circle. So which is pi into 0.1 the whole square, times cos of theta is cos of 60, which is half. Simplifying this, we get the value of phi to be 0.063 minus 0.013 into T. So this is the final expression for flux. Let's move on to the next question. Calculate the numerical value of the induced EMF in the loop. Here we can find out the induced EMF from Faraday's law. Faraday's law tells us that the induced EMF epsilon is equal to the negative of the number of turns N times the differential of rate of change of magnetic flux, or d phi by dt. So here we know the magnetic flux phi b. So we can just differentiate this equation. EMF epsilon is equal to negative. Number of turns is 1. So 1 into, when we differentiate this expression, 0.063 is a constant which goes away. Differential of AX is A, or differential of AT with respect to T is just A. So minus into minus 0.013 into 1. So simplifying this further, I get the EMF epsilon to be 0. Plus 0.013 volt. EMF is obviously measured in volt. For part C of the question, we are asked to calculate the numerical value of induced current in the loop. The induced current I can be just calculated as V by R. Here voltage V is nothing but EMF epsilon. So epsilon by R. R has a value of 50 ohm, as I've already noted down before. So this gives us the value of I as 2.6 into 10 to the power of minus 4 ampere in its SI unit. What is the direction of induced current in the loop as viewed from point P? So we know that as the magnetic field B is decreasing, and this is the reason why current is, or voltage is induced in the coil, the coil will try to produce or induce in a current in itself such a way that it can produce an increasing magnetic field in the direction so as to counter the changing magnetic field. This, in fact, is obtained from a law known as Lenz's law. So this tells us that the magnetic field has to be in this direction and it has to be increasing. So to make up for this, using a right hand grip rule, we can find out that the induced current has to be in counterclockwise direction as viewed from point T, because this is the only way that an increasing magnetic field can be produced in the direction stated so as to counter the decreasing magnetic field, which is causing it to induce current in the first place. The two laws we've used here are the Lenz's law to find the direction of magnetic field and the right hand thumb rule or the grip rule to find the direction of induced current so as to produce magnetic field in the direction given. Now, we need to also calculate the energy dissipated. Energy dissipated E can be found out as energy is equal to power into time. Power has two different formulas we can use. We can either use I square into R into T or V square by R. V is nothing but epsilon EMF. V square by R into T. No matter which equation we use, we are going to end up with the same value. Here time T is 4 seconds, by the way. The value of energy is going to be 1.4 into 10 to the power of minus 5 joule. So this concludes the answer to our question.